Hello, my name is Brian Freno, and the title of my talk is Geometrically Symmetric Quadrature Rules for Singular Integrals in the Method of Moments Implementation of the Electric Field Integral Equation. In this talk, I will describe the singularities that appear in the test integral in the method of moments implementation of the EFIE and how we develop quadrature rules which can integrate these singular integrands. In the method of moments implementation of the EFIE, surfaces are discretized using planar or curvilinear mesh elements, and four-dimensional integrals are evaluated over source and test elements. The presence of a Green's function, however, yields singularities or near-singularities in the higher-order derivatives of the integrand. These occur in the scalar and vector potential terms. When the test and source elements share one or more edges or vertices, we have singularities. When the test and source elements are otherwise close, we have near-singularities. Many authors have developed approaches for addressing the singularities in the inner source element integral, which can be categorized as singularity subtraction schemes, singularity cancellation through variable transformation schemes, or hybrid schemes, which combine these two schemes. For the outer test element integral, existing approaches include taking the outer product of one-dimensional quadrature rules, or performing a series of variable transformations and reordering the integration. Approaches have also been developed for the MFIE and CFIE. In this work, we present an approach for developing geometrically symmetric quadrature rules, and we provide a characterization of the logarithmic singularities in the test integral. I will now describe triangle quadrature rules and our approach to constructing rules for arbitrary function sequences. As you may recall, an n-point quadrature rule exactly integrates a function sequence consisting of nf functions. In one dimension, nf is 2n, and for polynomials, we can integrate polynomials up to degree 2 times n minus 1. However, in two dimensions, we can only speculate about nf, which may be further reduced by placing constraints on the rules, such as symmetry. Quadrature rules are rather challenging to generate. Regardless of the number of dimensions or the function sequence, the equations for computing the points and weights are stiff and highly dependent upon the initial guess. Furthermore, in multiple dimensions, for a given number of points, nf is unknown. The convenience of using triangles to discretize surfaces motivates our desire to employ quadrature rules for triangles to evaluate surface integrals. Several authors have computed symmetric rules for polynomials. However, polynomial rules do not converge monotonically or rapidly for singular integrands. Nonetheless, for one dimension, rules have been developed for singular functions. We prefer that the triangle rules are geometrically symmetric. Symmetry makes mapping one triangle to another straightforward, and points are not more concentrated at a single vertex. Symmetric rules are invariant to rotation and reflection about the medians for equilateral triangles, which can be isoparametrically transformed to other triangles. Symmetric rules are constructed using a combination of orbits, where a type 0 orbit consists of the centroid, a type 1 orbit consists of 3 points, each along a median, and a type 2 orbit consists of 6 points, not along the medians, but reflected about the medians. We developed two approaches for computing symmetric triangle rules for arbitrary functions. For our first approach, noting that our goal is to efficiently integrate polynomials and singularities, we compute points and weights through optimization. We use the polynomial rules as a baseline, both as initial guesses and with the same orbit counts for each number of points. Our function sequences are determined by replacing higher polynomial degrees with singular functions, and we attempt to increase the number of functions we can integrate exactly. For a given function sequence, we formulate the problem as an unconstrained, nonlinear least squares problem in barycentric coordinates with the expectation the objective function is 0. Because of the physical application, we only allow solutions that yield points inside the triangle. To construct the function sequence, we exchange higher polynomial degrees for singular functions. Polynomial rules can integrate cross terms such that, for example, the ability to integrate x cubed includes the ability to integrate x squared y. However, this capability does not extend to singularities. Therefore, one can use two-dimensional characterizations of the singularity if they are available, a one-dimensional characterization of the singularity, assuming the cross terms are not essential, or one can use cross terms for the one-dimensional characterization at the expense of further reducing the maximum polynomial degree. Alternatively, one can use our second approach. As I stated earlier, in multiple dimensions, the number of integrable functions is not straightforward. Computation of the rules is expensive, and multiple solutions exist. Therefore, for our second approach, we employ one-dimensional quadrature rules. For this approach, we divide the triangle into three quadrilaterals, each of which contains the points arising from the outer product of the one-dimensional rules. If we use n prime 1D points, we will have 3n' squared points for the triangle. Now I will discuss the logarithmic singularities which appear in the test integrand of the EFIE. Here we see the forms of the singular integrals in the EFIE when using the method of moments. The first equation appears in the scalar potential, and the second appears in the vector potential. R is the distance between a point on the source element and a point on the test element. When r approaches 0, the e to the negative jkr divided by r term is troublesome. We first consider the scalar potential. When the basis functions are Rao-Wilton-Glisson basis functions, or otherwise linear, their divergences are constants, and a series expansion yields integer powers of r beginning with -1. The odd powers of r yield unbounded derivatives along the boundaries of the source element. The even powers of r remain smooth and integrable. For the vector potential, if we assume unnormalized RWG basis functions, we get a parabolic type dependency upon r, for which a series expansion again yields integer powers of r. From these observations, we note the significance of the integral of r being raised to an integer power. When the power is -1 and the test and source elements are coplanar, we get the expression on this slide. Approaching the edges of the source element, such that beta equals 0 or gamma equals 0, we get alpha log alpha terms. At the vertices, alpha equals 0 and alpha log alpha is singular with unbounded derivatives. This confirms that shared vertices between the source and test elements are singular. Additionally, we can show that shared edges are singular. On an edge of the source element not at the vertices, alpha equals 0 and beta and gamma have opposite signs. Taylor series expansions of the logarithm argument lead to alpha log alpha terms, which we know are singular at alpha equals 0. Along an edge of the source element, a series expansion for q equals -1 as alpha goes to 0 yields a series of monomial terms as well as an alpha log alpha term. Increasing q to 1, we get alpha cubed log alpha terms, which also appear in the expansion. This trend continues for the other odd powers of r. Therefore, when the source and test elements share an edge, the shared edge and vertices have singularities. When the source and test elements are the same, the entire boundary has singularities. Now we briefly consider perpendicular elements. When q equals -1, we get the expression on this slide. Approaching the shared vertices from inside the test element, we get y log y singularities with y going to 0, similar to what we saw for the coplanar case. This trend continues for the other odd powers of r. It should also be noted that the arctangent terms are singular at the shared vertices, but since the coplanar case is more singular, we will tailor our approaches for it. Doing so results in points being more concentrated near the edges and vertices. This concentration improves the accuracy of the integration of the arctangent terms as well. We can develop a one-dimensional characterization of the singularity by taking a series expansion about the singularity location. This expansion alternates between monomials and singularities. From the coplanar and perpendicular cases, we get the monomials with the odd powers of x multiplied by log x. For the two-dimensional characterization, we use the terms we obtain from the coplanar case. Now, I will demonstrate the effectiveness of the combination of the quadrature rules and the function sequence choices. For these cases, for convenience, we assume the wave number is real and the wavelength is 1 meter. We have a test and source element, each the same size triangle, with in-plane and out-of-plane offsets in different relative angles. The scalar potential and vector potential are separated into sine and cosine components, with the cosine components being singular. We compute reference solutions using Mathematica. Here are the 1D and 2D characterizations of the singularities I mentioned earlier. These are the points for approach 1 using the 1D characterization for the singularities for 3 to 16 points. Note the clustering near the edges and vertices. Here are the points for 25 through 42. Once again, all points are within the triangle. These are the points for approach 1 using the 2D characterization for the singularities for 3 to 16 points. And here are the points for 19 through 52. For approach 2, this is the 1D function sequence I described earlier with the odd powers of x times log x. Here are the points for approach 2. For the first case, we have two coplanar elements which share an edge. The left figures show the performance of multiple quadrature options for different amounts of points. The top figure is for the singular cosine integral, and the bottom figure is for the non-singular sine integral. We integrate the source element integral using Kayat's radial angular transformation. For the test integral, we consider the traditional polynomial rules in red, our approach 1 with 1D singularities in green, our approach 1 with 2D singularities in blue, and our approach 2 in purple. The orange DMRW rules are an existing approach which use 1D rules that integrate all powers of x times log x. The outer product of these 1D rules is then asymmetrically mapped to the triangle. Because of this asymmetry, we have plotted the average performance of each of the three possibilities. In the upper figure, we note the inconsistent performance of the polynomial rules, which perform fine below for the non-singular integral. In general, approaches 1 and 2 perform quite well for the singular integral, orders of magnitude better than the polynomial rules. Finally, in the lower figure, we note the rapid convergence of our approaches for the non-singular integral. These trends continue for other angles, including 45 degrees, despite the rules being developed for the coplanar case. For 90 degrees, we see similar trends. Finally, at 180 degrees, the source and test elements are the same, and we see the trends from before. Next, we add a tiny separation between the two elements, which causes the cosine integral to be nearly singular. Note that we have exaggerated the amount of separation on the right figure to make it easier to see. Our approaches were not designed for this case, but they still perform competitively. We now consider a Farr interaction with the separation understated in the right figure. For this case, the cosine and sine integrals are both non-singular and the polynomial rules perform fine. Nonetheless, approach 1 has an efficiency similar to the polynomial rules. Finally, we consider the vector potential, for which we observe similar trends to what we saw for the scalar potential. Here is the 90-degree case. And here is the 180-degree case, with the test and source elements being the same. To summarize, we introduced two symmetric quadrature approaches for arbitrary functions. These were motivated by our need to integrate the singular test integrands in the EFIE. Our first approach is generally more efficient and outperforms the polynomial rules by orders of magnitude for singular integrands. For non-singular integrands, it achieves similar efficiency as the polynomial rules. Our second approach is also more efficient than polynomial rules for singular integrands, and the error decreases monotonically as we increase the number of integration points. These points are also cheaper to determine than the points of approach 1 since they arise from 1D rules. If you would like to read more about our work, we have written two manuscripts. The first describes the quadrature rules, and the second describes the singularities in the EFIE. Thank you for listening to my talk.